Alright, so in this video I'm going to continue our discussion on graphs involved in motion. In the previous video we went on to discuss how graphs to form x versus t, that is displacement in time, and using that we were able to evaluate velocity. Now what we would do is we would plot velocity versus time. So we would plot, rather than x versus time, we'd actually plot v versus time. From the x versus time graph. So we would take information from x versus time graph, use it, modify it, and then plot it again to v versus t. And then using v versus t, we'll try to retrace back into how we actually can derive x versus t from v versus t. So in a sense, let me just get rid of this. What we're trying to do is we're trying to interconvert two forms of graphs, one that we have studied and one that we will study or we will discuss. First one is something that we have already done, that's x versus t, and say the graph looks something like this, some curvy thing like that, but that's good, that's displacement and time. What we'll do is we would use that information to get some form of v versus t, so we might get something like this, and I don't know, this, something like that. We'll discuss how we can get v versus t from x versus t, and we'd also discuss how we could get x versus t from v versus t. So to clarify what we are actually talking about, we are talking about displacement versus time, and we are talking about velocity versus time, right? So let's begin. So in the previous videos, we have discussed what x versus t graphs signify. This is the x versus t graphs form, and we know that if, say, x versus t graph goes like that, and that, same form, exactly the same form as what we took in our previous video, such that at t equal to 0, the position of the body is at x equal to 5 meters, t equal to 2 seconds, which is here, t equal to 2 seconds. The position of the body is at, well, 10 meters. T equal to 3 seconds, the body goes back to 0, so right there, 0 meters. T equal to 4 seconds, it holds that position at 0, and at t equal to 5 seconds, so 5 seconds right there, it goes back to, well, 5. So there you have it. That's the x versus t graph that we would be using throughout the video. All right. So we ended up finding out that the velocity vector is actually given by dx of t by dt. That's the derivative of this line, this function. This is an f of t function. It's basically x of t function, the position versus time. And if we take the derivative of this function, this orange line, at all times, we evaluate the velocity. Oh wait, this is a velocity vector on the left-hand side, but on the right-hand side, we simply have a scalar because it does not include anything in terms of direction. So in order to compensate for that, we must add an I cap there. So that is to say that if our position of the body only moves in one dimension, that's in the x dimension, velocity simply points in the same dimension. That's also in 1D, and you get velocity as velocity comes out as v of t from this formula. So the slope in the direction gives us the velocity vector, or simply the speed is given by, well, dx of t by dt, and you take the modulus of that. You disregard the I cap there because now you're talking about speed, not velocity. It's a scalar, not a vector, and you simply take the modulus of that because speed can never be negative because it's a scalar. So with all those in mind, all those things in mind, what we can do is we can evaluate what v versus t would be. Now we have done this in our previous video. I'm just going to repeat it for completeness sake. And what we're going to do is we're going to evaluate the slopes at different line segments. So the first line segment that we're going to consider, it is x versus t graph is the line segment from 0 to 2 seconds. So that's this line right there. All right. So what we are actually getting out of that is the velocity vector. So I'm going to do is I'm going to take t there. I'm going to take v there. So this is the velocity. Now, keep in mind that this velocity vector, it's a vector. So it comes with a sign, but we won't be able to plot those vectors in on a coordinate. So this is not exactly a vector, but is not simply a scalar too. It's not speed because of the fact that velocity can take negative values as well, as you would see in the time segment 2 to time segment 3. And it's not simply a vector because we are not considering directions. it's just being represented on a 1D plane. So this is a different kind of notion of speed. It's basically speed with sign. This is what I refer to V. But it gives us every information that the velocity vector would be able to give, and therefore we simply regard this as velocity itself. So what we're plotting on the y-axis here is the velocity, and on the x-axis we're plotting the time. It's a modified velocity. Keep that in mind. Now, with that thought in mind and embedded in your thinking, it's good to proceed on. So the first thing that we're going to do is we're going to consider this line segment right there, this one in red, and the slope of that, because of the fact that we're evaluating velocity, would be, well, this height divided by this length, and that gives us tangent of this angle. So that slope, the first slope, if I write slope between 0 to 2 seconds, comes out to be, well, this height is 10 meters minus 5 meters, and this length is, well, 2 seconds minus 0 seconds. So that gives us 2.5 meters per second. That's the velocity that the body holds for the first 2 seconds. And why do I say that the body holds that velocity for the first 2 seconds? It's because you see that the slope doesn't change throughout this motion. It holds a constant value. And the reason I say that too is because this line, this geometric shape or entity is a line. It's not a curvy thing, it's a line. It's a line that holds a slope throughout. So with that in mind, we know that the velocity of the first 2 seconds of the body would be positive 2.5 meters. So in order to do that, what we could do is we can plot 0 to 2 seconds of time on the time coordinate, and on the velocity coordinate, we must specify that with a velocity of 2.5 meters per second, and we must hold that constant throughout the 2 seconds. So this implies that for the first 2 seconds, the velocity was a constant, and the reason it's a constant is because the reason you see it's a constant is because this height here is constant throughout its motion from in the first 2 seconds. So that's the first slope. What about the second slope? The second slope for the second segment. So the slope for 2 seconds to 3 seconds. Well, we can evaluate that in the same manner as we had done before. We considered this height, but in the negative, and this length, again, but that's in the positive. And we do that with the height being, well, 0, because the body is at 0 here, and at 10 there. So it's 0 minus 10 meters divided by 3 minus 2, that gives you, well, that's in seconds, so that gives you negative 10 meters per second. So the second velocity, so the second set of velocity would be negative 10. So in order to do that again, we take 3 seconds there, and now we must plot negative 10 rather than the 2.5 that we did earlier. So if I go back in the negative direction, I must get a negative 10 meters per second somewhere there. I must extrapolate that and hold that for the 2 seconds, for the 1 second that the velocity would be. So my velocity is like a discontinuous graph or discontinuous line, and in order to account for that, what we can do is we can connect a vertical line like so. So this is a velocity sketch for the first 3 seconds. The first 2 seconds, the velocity was a mere 2.5 meters, but for the last 1 second, it was a tremendous negative 10 meters per second, but that was in the negative direction, and that's why it steps down. Now, we can repeat that for the next segment, so that's slope, or the velocity, from 3 seconds to 4 seconds, and that comes out to be, if we need to evaluate that, we need to evaluate the slope of this. Now, you can eyeball this right away. You see that the slope is 0 because the line is not going up or is not even going down. It's just holding its constant. So the slope here must be 0. And you can also count that by taking the difference in y-coordinates. The y-coordinate at this point is the same, and the y-coordinate at that point is the same. That is to say that the distances or the displacement at both these time intervals, or anywhere in between for that matter, is the same. So the difference in any of those points, y-coordinates or the displacement coordinates, is 0, and the time interval is, well, 1 second, because we're considering 3 to 4. That gives us 0 meters per second. So it doesn't matter what the time interval is, because the numerator is 0. That means for the next 1 second, that is from 3 seconds to 4 seconds, the body holds a velocity of 0. So again, it's a discontinuous function and comes down to 0 from 2.5 and goes up from -10. So you must also connect this vertical line as well. Keep in mind that the vertical lines don't really mean anything, because the vertical line are just connecting the line segments to indicate that the velocity abruptly changed from one interval to the other. So the only sense that you can make from this graph are the horizontal lines, or anything but the vertical lines, because vertical speed vertical lines in v versus t really don't make sense. All right, they just give you a sense of how things get connected, but that is to say that there was a very abrupt change. So with that in mind, what we can do is we can evaluate the slope for the next 1 second, and we're going to do that like we had did in a previous video as well. So that's 4 to 5 seconds, and keep in mind we need to take the difference in the height, that is this particular height, and that's 5 meters, and divide that by 5 minus 4 seconds, so that's 1 second. That gives us 5 meters per second. So this is a positive value. That means that we must plot this on the positive side of v, would be somewhere there. So for the next 1 second, that is from 4 to 5, we must plot our velocity right there. So a dotted line to help us plot it, but a solid line to actually plot it in that time interval. We must also join this line like that. So you see, this function is giving rise to another function. This function of x versus t is giving rise to a function that we call v versus t. That's displacement function is giving rise to velocity function, and you see it's a very abrupt thing, and the velocities change very rapidly. For the first 2 seconds it's plus 2.5, then it goes back to -10, then it goes to 0. At this point, the body is at rest. And the reason we say that is because the velocity is constant. After 1 second of rest, the body continues to move abruptly with 5 meters per second in the positive direction. And if you want to plot it further still, well, the slope is 0. That is to say that for the next seconds, till whatever time this solid line holds, the slope would be 0. That is to say that the body goes back to rest again for every time instant after 5 seconds. So that is how you get v versus t out of x versus t. So we have gone a one-way route from x versus t to v versus t. That's how we ended up plotting this. So keep in mind that this was a very simple case where all the lines were straight lines, and hence the slopes were constant over intervals of time. That is to say, it was constant from this interval, that interval, that interval, that interval, and that interval. It wasn't constant in the first 3 seconds because it varied from plus 2.5 to -10, but for some seconds it did hold constant. And that's because we ended up drawing the x versus t as straight lines. Now things get more complicated if you draw a more curvy line like so. If I get rid of this, and just to illustrate what x versus t could look like, say we have a car that starts moving at 0 time. It was at the origin, so it was right there, but then it starts to move. Now it doesn't abruptly change its position, but rather does that gradually, in the sense that it accelerates for the first few seconds. So let's say it accelerates till there, and when it does that, it develops its speed, and the way we show that is through a gradual incremented slope like that. So that is how the displacement would look like. Initially, the car was, well, you see this very small distance, that's where the car was. For the next time interval, well, the displacement increased, and for the next segment, the displacement increased still further, disproportionate to the increment in time. This is what we call acceleration. Now, you don't have a straight line. That is to say that the car didn't hold constant velocity for this interval of time. It increased its velocity from 0 to a certain amount. So you don't have a straight line, but you have a line that curves upwards, and this upward curve represents positive acceleration. So let me just write it there. We'll go into detail regarding this concept later on, but it's just good to know. So the first few seconds of the motion, the car held constant acceleration, or basically accelerated, held an increasing velocity throughout that, and after some time it held that constant velocity. So if you want to hold a constant velocity, that is, you want this kind of a function as v versus t, and that translates into an increasing line in x versus t. So in order to do that, we must have a straight line for that time interval. So we limit our straight lines there. So for this period, we have constant velocity like that. That's because the slope is constant, it's a straight line. Now, with that in mind, we want the car to stop. So now that the car started moving, it increased its velocity at different intervals of time, and then further on, it held a constant velocity but kept moving away from you. That is to say, it kept developing this height in time, and at some amount of time, after some amount of time, it wanted to stop. Well, if it wanted to stop, the only way it could have done that is if it started to deaccelerate or retard. And retardation is basically negative of acceleration. And basically what we need to do with that in order to plot that is, what we will do is we will take a negative curve, or like a curve that ultimately becomes flat in this manner, but does that gradually, very much so like the first interval of time over which the car accelerated, but all that in negative. So you see that after this, it changed its slope. Its slope was this initially, then its slope became that, and finally the slope became that. And when it was there, it stopped. So if it stopped, we know that if something is constant and is at rest, then it's not moving in position at all. And if that's the case, then we know that whatever displacement it had acquired until this point of time, it would have held this displacement through the rest amount of time as well. So that is to say, it would not have moved. And this would have meant that the body is at rest. So that is your rest state. That is to say, because the slope is 0. Slope is 0, that means velocity is also 0. Now you see, your velocity is constant here, velocity is not constant there, and it's not constant there, but it's constant there, and it's constant there, because the velocity is 0. So that is how a car would look like. And you see, the reason I illustrated that is because it's very different from what we found here. These are very abrupt changes, but you get more gradual changes in reality. So we can still plot what happens to velocity as it changes in these complex situations, but it would not look as beautiful or like as simple as this. Anyway, now that we are done going from x as a function of t to v as a function of t, we could try to plot it back. And that would require a bit of discussion, which has to do with calculus. So this is a bit that requires a bit of calculus to really understand what's going on. So there you have it. Now, we know that the velocity vector is given by dx by dt I cap. So if what we were plotting here was just v, so it's just v without the vector, it's still velocity. It's like speed with a sign. So that's basically dxt by dt. Now you see both these quantities match. They are scalar on the left hand side and on the right hand side, but they both have signs as well. So this is what we were plotting there. This was not v of t. This was also not speed, but this was simply velocity, like in that sense. Right. So this was how we had gotten velocity from position. In order to do the reverse of this, we see that we must do something like this. Integral of v as a function of t dt would give us integral dxt, like that, or basically x of t. So integral of v of t dt gives us x of t. Now you see that this is a differential equation here. This is differentiation. And the reason we call that differentiation is because you have a derivative here. Now, in order to repeat, in order to go back and construct x as a function of v, rather than v as a function of x, this is how we do it, that we integrate on both sides with respect to the variable we differentiated with. So that is how you get this. Now, what does integration really mean? Integration means finding out the area. So this integral sign, this comes from calculus again. It basically means that if you want to know what x as a function of time is, you must evaluate the area at different time intervals. So the area is what we are evaluating in the v versus t graphs, not the x versus t graph. Now our aim is to find out x versus t from v versus t. So we have this situation here, and we wish to go back to the situation there. We don't have the situation right now, but we only have information about v versus t. So the only graph that we would consider while figuring out what x versus t would look like would be this here. Now, like I said before, we must evaluate the area in order to get back to this situation. The area is actually this area here. So this is the area that we would have to evaluate in order to get this line. you see that at different time on the t coordinate, the x versus t increases. That is to say that if I consider the area until this time, it was this. But if I consider the area until this time interval, the area was this. It was much larger than what I had gotten here. And that is to say that the area increases linearly with time. So if the area increases linearly with time, linearly means you must go with constant slope. And so that is how you get the velocity. Now, let us try to evaluate that in terms of what we have done so far. So we have this v versus t given, and let us evaluate the area of v versus t from 0 to 2 seconds, right? So let's try to do that. So the area would be this blue or this yellow kind of area now. The area would be the base multiplied by the height. That would be 2 seconds. That's the base. You multiply that by the height. The height is the velocity of this rectangle, and that would be 2.5 meters per second. So you see, that gives us 5 meters. What does 5 correspond with? Well, 5 corresponds with the displacement. It's not x versus t as of now. The reason that is because displacement measures the difference in motion. So what we are really asking ourselves, or what we're really getting out of evaluating this area, is how much the body moved in the first 2 seconds. So if you go back to the x versus t graph here, you see the body was originally at 5 meters. And finally, at 2 seconds, the body was at 10 meters. So the motion happened over a displacement of 5 meters. And I get that 5 from subtracting 10 meters from 5 meters. That is to say, I subtract this height from this height right there. I get this height, and that itself is 5. This 5, as what I get from x versus t, is exactly the same 5 as what I get from finding out the area in v versus t. So what's really happening is it's telling us how much the body moves. So even if our x versus t graph looked like this, starting from the origin going to 5, still holding a displacement of 5 in the first 2 seconds, this would have been the velocity versus time graph, even in that case. And that is to say that the net displacement in the first 2 seconds has been 5 meters, no matter where the body was initially. It could have been there, could have been there, could have been there, could have been there. As long as this height is held constant at 5 meters, this would have been the answer. Alright, so that makes sense. So the area, the net area that we get, gives us the absolute displacement, right? So let us try to use that further on for the next 1 second as well. So let us evaluate now the net area. Now that we have figured out the net area represents everything that we are trying to evaluate, the net area for 0 to 3 seconds. That is to say, we're considering motion from there to there. Now, what do we hope to expect? We hope to expect the displacement, the net area, should give us the net displacement in the first 3 seconds, from 0 to 3 seconds. Right there. So what we're trying to evaluate is the net displacement from 0 to 3. So the net displacement would have meant the final position at 3 minus the initial position at 0. So that will be x of 3 seconds minus x of 0. It's always final minus initial. X of 3 seconds is 0, as what you see in x versus t. But what is x of 0? Well, x of 0 is 5 meters, because the initial position of the body was at 5, this height. So the net displacement should have been negative 5 meters. Let us see if that is the case. Let us check if that is the case. So with a change in the color of my pen, I could now go on to evaluate the net area. Now, in order to do that, we must evaluate the net area in the first 2 seconds, and also include in that the area in the second, in the last 1 second. The area in the last 1 second is this. But you see, there's a difference between this block right there and this block right there. This block happens to be in positive V, or on the top quadrant. But this block here happens to be in negative V. So that means that the area that we consider here must be negative, but the area that we consider here must be positive. So we must add to this area the negative of this area. That is to say, we must subtract this negative area from this area. So let's try to do that. So the area in the first 2 seconds, and we must add to that the negative of the area in the last 1 second, right there. So a from 0 to 2 is something that we have already evaluated. That was the net displacement in the first 2 seconds, which was 2.5 times 2. That was 2.5 times 2 meters. Now we take the area in this block there. Now the area is a scalar and should not contain any signs, but we have already accounted for the sign outside, so we simply need to evaluate the area in positives. The height of this here is, as you would have guessed it, it's 10. So that's the height. And this here is 1, because that's 1 second. That's 10 meters per second times 1 second. So that's still 10. And that again is evaluated in meters. So our net area would be 5 meters from there minus 10 meters from there. And if you evaluate that, it comes out to be -5. So what we have gotten so far is the fact that the net area corresponds with net displacement. And the reason is because this term here, the net displacement, what we get from x versus t, comes exactly to be the net area from v versus t. So you see a correspondence, you see an equality. That is to say that the net area in v versus t corresponds to the net displacement in x versus t. And that is how you get the x versus t graph back from v versus t graph. So far, just to summarize everything that we have done, we have worked with, let me just change, yeah. So we have worked with x versus t, and we have shown that if you're given a graph of x versus t, that's position versus time, something like that, we have shown that the slope at every point, like that or like that, the slopes give you the velocity as a function of time. That is to say, the slope helps us plotting v versus t. So you get some graph for this. And what we have also shown is the fact that once we know what v versus t looks like, say v versus t, t like that, say v versus t looks like that, something like that, then we know that the area in some interval of time, the net area on a v versus t gives us the net displacement. And using that information, we can plot our x versus t graph back again. So we have shown how to go from x versus t to v versus t, and we've also shown how to go from v versus t to x versus t. So that is how motion is analyzed. That is how motion in one dimension is analyzed. So I hope this video made sense to you, and I hope it helped you to understand the importance of slopes and areas and how integral a part calculus becomes when we deal with complex motion. In further videos, we will try to work onto this concept and try to include another topic of acceleration, and using that we will try to reevaluate and rederive these 3 equations of motions that we ended up finding simply by calculus and vectorial algebra. So I hope this video made sense, and all the very best.